I'm back again and I'm reviewing one another paper that is mini Omni language models. Mini Omni language models can hear and talk while streaming, while thinking in a streaming, right? So recent advances in language models have higher significant progress. GPT-4 O has new milestone has enabled real-time conversation with humans, demonstrating near human natural fluency. Such human-computer interaction necessity model with the capability to perform reasoning directly with the audio modality and generate output in streaming. However, this remains beyond the reach for current academic models as they typically depend on extra TTS. Okay, so we call this training method any model can talk. We introduce the voice assistant for 400k dataset to fine tune models optimized for each output. To our best knowledge, Mini Omni is the first fully end-to-end open source model for real-time speech. Okay, let me see. I mean, what it is and how we can interrupt this. So naturally we have a GitHub repository of this particular research paper. So recent advances in language models have achieved significant progress. GPT-4o, a new milestone, has enabled real-time conversation with humans, demonstrating near human natural fluency. Such human-computer interaction necessary models with capability to perform reasoning directly with audio modality and generate output in streaming. However, this remains beyond the reach of current academic models as they typically be dependent on extra TTS system for speech synthesis, resulting in desirable latency. This paper introduced Mini Omni and an audio-based end-to-end conversation model, which is real time. Okay, so we call this any model can talk, voice assistant 400k, Mini Omni. Okay, and streaming output is high. My name is Omni. This is output. Then parallel generation is there. Okay, so we have wave. Wave is essentially an audio. Okay, so there it is whisper encoder, audio adapter. Then many Omni language modeling. In language modeling, what we do is parallel generation, and that text and audio tokens are already there. We have taken. Then streaming audio decoding. Then we can divide it into the numbers, or maybe we have already read in previous paper that we can divide it into number amending, or maybe you can say what I'm acronym the term is not maybe right, but it is positional encoding and maybe right word encoding. We have seen the two models, word to vocabulary, and other models rated on this only. So we can divide it into positional encoding. Hi, my name is Omni. Streaming output is this, right? The Omni model architecture. Okay, so the recent language model have progressed rapidly, with models becoming increasingly shelf Llama 3.0 Mixtral, Queen 2, and well-known GPT-4. Okay, so it is complexity of audio reasoning, difficulty in model alignment, resource demand, model complexity. Mini Omni is this, and batch-based parallel generation. Okay, so we introduced Mini Omni, the first open source end-to-end multi-model large language model with audio and input streaming output capabilities. Any model can talk. Okay, so recently researchers have been increasingly focused on advancing unified model for cross-model understanding. These models typically employ a well pre-trained neural network as encoder for modality. So it is Lava, Flamingo, Blip for visual understanding, Whisper, and Beats. Right? Our model commonly utilize an encoder for semantic and acoustic features. Right? In Llama 3.1, Whisper is employed, while speech words leverage Lam and Salmonen. Okay. So recently, an increased number of studies have employed audio tokenization to bridge gap between audio and text. Audio tokenization converts continuous audio signals into discrete audio tokens, enabling large language model to perform inference and even cross-model interactions. As a result, variety of speech text such as ACR, TTS, music understanding, and generation sound editing can be accomplished. Mega TTS utilize audio codes for speech synthesis, while effort like Inceptor TTS and Spear TTS and voice box have further explored optimization in decoding methods and combining techniques. So real-time human-machine interaction models are already there. Speech GPT, we have another thing, LoRa GPT, Vita, Mini Omni, right? Mini Omni is already there. We have defined the output. Consider y is belong to v. V is verbal text of maybe anything. We have a strange criteria, maybe independent variable v text. I equal to 1, so t as a text occurrence for vocabulary v text with the length t text, right? The probability of y can be extra that probability of y output, right? So t text y equal to 1, p starting from y I equal to y I minus 1, right? So it is a, you can say it is a sigma, but it is not a sigma. It is like I'm on the page number 4 reading audio language modeling, right? So now when dealing with the continuous speech and signal, we encounter discrete speech tokens represented as D to DIV DST using a tokenizer. In this token vocabulary of discrete speech tokens, these speech tokens can be treated as spoken language within VDST and modeled in manner similar to text. Text is in vocabulary view text. Okay. So again, probably we can divide the particular PZ into different. VO text is VDST. Okay. So error disturbance. Lead T A upon C. So we can divide into I into J. Log P Ti we can divide into two logs. T is less than Ij and A is less than Ij Xj, right? So what happen here, we can combine in text and speech, right? Which with the verbal text and the VOXT with V text and U TST, right? Therefore we can model the probability of both speech and text tokens as Z, right? From Z we can model both speech and text tokens. Z is belong to verbal text token I equal to 1 T. This probably is expressed as PZ Ti P1 ZZ. We can divide Z as represent discrete speech tokens as D Z. We can represent Z as a discrete speech tokens and V equal to DST, right? Text token is Y equal to VXT. So various combination of Y and D for the audio and video audio and text token generated simultaneously. The negative log likelihood loss can be formulated as in equation 1, right? So we have another variable now. It is L T A upon C, because we want the text and audio synthesis, and we MN and criteria is there. Log P in this criteria. So text delay parallel decoding is this. For real-time speech output models, parallel decoding is even more critical. So we can do is this, right? Parallel decoding with text instruct, batch parallel decoding with text instruct. Here it is mini omni. It is music generation, right? So although the previously introduced parallel generation model effectively transfer reasoning complete from text model to audio mobility, our experiment revealed the model reasoning hypothesis still varies between text and audio tasks. When we see the parallel decoding in music generation, there are two criteria. First is in decoding step, text token is there. I'm on page number 5 reading decoding steps, right? So naturally what happened that in second option we can see it in with the text instruct little disturbance in text instruct, but we see that in batch parallel decoding with text instruct we see that, right? Okay, so this is how we can see in every different models. So it's a this issue for the required text response focusing on text sample model. Any model can talk. So this is how it is. adapter, whisper encoder, wave text embed, text adapter, wave text whisper adapter. Yes. Okay, maybe I need to explain further. So mini omni is just a criteria we use, right? So ASR adapter embed, whisper, wave text embed, and this morality element, LM adaptation. Okay, so we can see that how we can text to text, audio to text, and text to audio, and audio to audio, right? So different kind of inputs are there, right? So we are expanding doing the experiment, right? Open Orca, mouse accepted dataset, and voice assistant and something like text QA, mouse, and this. Okay, A T1 T2, this one, right? Experiment result, we have decoders also. So this one, what is your name? Then my name is Omni, I'm real time voice assistant. And then again, this is a case study where encoder decoder model is applicable. There are different methods: view to see base, beta, research respond, mini omni, right? So we can do that. This is how it is. Conclusion: we introduced mini omni, the first multi-model model, direct speech to speech capabilities. We can test that from audio and text speech, and we can find out that audio is different and text is different. In terms of speech recognition, we have criteria. We have already discussed earlier. We explore both text and streaming and parallel generation, right? Any model can talk much. Okay, so we have the GitHub repository for that. You can check it out. Your GitHub repository also. Adaptation training, adapter embed. Okay, so this is how it is that I have explained you this model. Many Omni language model can hear, talk while thinking and streaming. Thanks.